Hello everybody! I'd like to demonstrate my Earthship inspired SAS project. SAS meaning Simple As System. I call this the WAM module, Water Automation Module if you don't like acronyms. It's an experimental project. By no means am I a professional. I just know enough to tinker. This system is intended to automate a water supply to micro sprinkler systems in a greenhouse garden. However, it's a proof of concept that can be used for other applications, and it can be added to supply power or water to other features. It's pretty cool how much you can do when you build your own circuits. Before I show you the system, I'd like to go over some of the components in it, just so we have a general understanding. This is a timer switch. It has a display screen and buttons for you to set your pre-programmed schedules. This particular timer that I have in the circuit, you can have up to 17 schedules for any of the 7 days a week or multiple days. How this works electrically, it has a power side and a switch side. The switch side is normally open, meaning that when there is no power supplied to the device, the switch is open, meaning that it will not send any power to the devices connected. How I've wired this is I've sent 12 volts DC to the power side as well as the switch side, and I've also supplied a neutral to the power side. When a schedule is activated, the switch closes, sending power to all the connected devices. Next on the roster, we have a relay switch. Single pole, double throw, meaning that it takes power from a single source and it throws power to two sources. So how this works is there's a coil side which is isolated from this side, but the coil side will activate a switch between these two outputs. So I supply 12 volts DC to the coil as well as the neutral, and I also supply 12 volts DC to this common wire. So these two outputs, we have a normally closed, so when there is no power supplied to the device, it is connected to this common. When there is power supplied to the device, it is not connected to the common. I don't use that lead. The lead I do use is normally open, so when there is no power to the device, it will not send power to any of the components connected. When this coil is activated, the switch gets connected and it connects this common and normally open lead, sending power to all the connected devices. This is a water valve, also known as a solenoid valve. It is normally closed, meaning that when there's no power to it, it will not allow water to pass through. How I have this in my system is I supply 12 volts DC to it as well as a common neutral wire. When it is activated, the valve will open, allowing water to pass through. Pretty simple part here. We have the pump. The pump in this particular system only takes 1 amp of power, 12 volts DC, and it will output 206 gallons per hour, which is 3.4 gallons per minute. Also, if you like liters, it pumps out 780 liters per hour. Pretty simple. Power is supplied to the device. There's an internal motor on the inside that spins. It will take water from the inlet and pump it to the outlet. The outlet will be connected to the micro sprinkler systems that will water the garden. Typically, sprinkler heads in the micro sprinkler system will output between 1 to 10 gallons per hour. And if you get the right ones, you can get ones that are adjustable. So you can adjust them between 1 and 10 gallons per hour, depending on the plant's needs that you're watering. The last component I'm going to show you is a float switch. I have two diagrams here. This is one component, but it's just drawn twice. So on this side, the float switch is closed, meaning the water level is above it. So this float will stay up, closing the circuit. There's two wires supplied to this circuit. One is the common, or one is the 12 volts DC, and one is the neutral common. When it's closed, electricity can pass through it. When water drops below the float will drop due to gravity, and then electricity can no longer pass through it. Before I show you the actual circuit, I want to run you through the wiring diagram, and I will draw on this to depict how electricity will pass through it. Let me zoom in a little bit. There, that's a little better. So on here I have the 12 volt DC line, and I also have the common neutral line. So the first components that are connected to the power are the timer switches. So I bring power to the power side of these switches to energize the components within them, the internals. And I also supply power to the switch side. And everything needs to be grounded or have a neutral wire too. So I also supply the neutral common wire to them. So these switches, timer switches, have power to them all the time. Like I said, they have an internal battery in case if they lose power, they will still be able to store your program schedules. When the schedules are activated, let's just pretend this switch is activated and the other one is not. So a schedule within the switch is activated, and it will send power to the water valve, solenoid valve, and it will also send power to the relay switch. And the relay switch gets power to the coil and as well as to the common. So the coil is energized on the relay switch, and it connects the normally open lead with the common. So then it becomes closed, and then it will send power to the pump. Now the reason why I have a relay switch for each timer is because when one timer is activated, this relay switch is open, so it will not allow power back to the water valve. You do not want water coming out of the valve for the water circuit where the timer is not activated. So that's the purpose, and that demonstrates why I needed to have relay switches. To finish this, everything is connected to a common neutral wire. So the valve, the relay switch, and the pump are all connected together, and in order for them to be grounded or to go through, the 12 volts is not 12 volts until it can actually go through to the other end. We have that safety float switch. And the reason why I did it this way is because that float switch, it cannot take a heavy load. So instead of putting all this stuff after the float switch, I just bring their grounding or their neutral through the float switch, and that way the float switch isn't under any load. It just opens and closes the neutral wire. So all those are connected. As long as the water level is above the float switch, it will allow those circuits to close, energizing the components. So when that timer is on, it sends power to the water valve and the relay switch. The relay switch then throws power to the pump. So all those devices are activated, the pump is on, and it will take water from its source and pump it to water plants. The same thing happens on the other side. I won't go through it because it's exactly the same as what we just went through. But without further ado, I will show you the actual circuit that I made for this. Okay, this is what the system looks like. This is a small 9" by 9" board. I actually used a pizza box and I plan to just throw this inside an electrical box. So we have the timers here, and these are terminal strips. They allow you to connect several wires together. As you can see, there's wires everywhere, so it'd be kind of hard to demonstrate what I did on the wiring diagram, but the wires flow exactly how the wiring diagram showed. Here we have the water valves, 2 of them. We have the relay switches here in the center, and we also have the float switch. See, this will close the circuit so that it works. When the water drops below, the circuit will not work. It's a good protection device so your water pump is not running dry. So all these parts are fairly inexpensive, between like $10 and $15, maybe $30 for the timers. I can't remember, but they're all fairly inexpensive. The pump here probably costed a little bit more. Maybe it did cost around $30 or so. But they're all really low consumption devices. I've designed it to work off of a 10 amp hour 12 volt DC battery and a 10 watt solar panel, which is pretty awesome. So you really don't have to have, this could be a completely isolated power system. You just have to get a small battery and a small solar panel if you didn't want to connect this to your main power system of your house. So with these terminals, you see they're connected. These are crimp connections. You have to have a crimping tool to connect them to the wire. I don't know exactly what they're called, terminal crimps, something like that. They just go on the ends of the wires and they connect everything. This is a voltmeter. I would highly recommend you have one if you're going to take on a project like this. It allows you to test things. Like here we have the continuity test that just allows you to see whether or not wires are connected. It'll beep when they're connected. And it can also test the power. So if I turn it on to 12 volts DC, and let's just pretend this timer turns on. It's not actually connected to the pump, but it's connected to everything else. So there should be 12 volts DC supplied here now that the timer is activated. And as you can see, just above my hand, 12.33. So highly recommend you have a voltmeter, also called a multimeter. It's pretty handy to have. I use it for a lot of things, and it was especially really handy for this project. This system might be a little too complicated for some applications. You can easily go to the hardware store and get a timer water valve. But what I'm demonstrating that you can do when you build your own circuit is you can add on to it, and you can add more things. For example, with this circuit, I could also add on a voltage cutoff. If your system is supplied by a battery, let's say the battery drops below a certain voltage, we want to shut the system off to protect the battery. This could be extended to have as many water lines as you want with pre-programmed schedules. It could supply a water feature. Let's say you put a small waterfall feature in your garden. You can do several things with circuits. There's more components that you can get that enable you to do cool things. But just saying, you could really just get a valve at the hardware store. But if you like to tinker and you want to do more things and be hands-on with it, I highly recommend doing something like this. Here I'll demonstrate how the water is all connected. This is for an off-grid application, so we wouldn't have that much pressurized water. It might only be like 1 to 10 psi, depending on how big the water tank is. So that's why we need this circuit. If you do have pressurized water, you wouldn't need all this. But being that we're off-grid, trying to live sustainable, we have this water tank installed outside. It could be a cistern or a rain barrel, anything that will hold water. If you don't have access to install the float switch inside the tank, it's okay. You can just install it anywhere and just install it at whatever level you want it to cut off relative to the water tank. So here, we have it installed at this level. As soon as the water drops below this level, the circuit will shut off. So what I'm doing here is I'm coming with a 1/2 inch PVC from the water tank. I tee off to the float switch. The float switch is a 1/2 inch threaded, and I was able to find this nice T piece. This is 1.5 inches, so I'll have to reduce it down to 1/2 inch. But there's a threaded piece for the 1/2 inch. This is a female. The male threaded 1/2 inch pressure switch will be able to screw right inside there, and I'll be able to just install this at whatever level I want the water to shut off at. But I just wanted to show you this piece here. Pretty cool. So after the float switch is installed, I continue on and bring the water to the pump. The pump is attached to all these water valves. This is the bonus of this kind of a circuit, is that you only need one pump and you can run as many water lines as you want. The question is how big does the pump need to be? So these will turn on and off. Anytime anyone is opened, the pump will also be on, and it will pump water through the valve to the garden. And let's say this one is on, this one is off. Water will not go through this one, but it will go through this one. So that allows you to have your programmed schedules. In addition, I wanted to show you these tiny micro sprinkler water lines, you'll be able to have several of these teed off of the main water lines that go from the valve. And these are just really, really small sprinkler heads. And the cool thing about them is that you can twist these to adjust them from 0 to 10 gallons of water per hour. And you can get all kinds of sprinkler heads. You can get spray systems, drip systems, you can even get mister systems. Whatever the needs of your plants are, you can get different kinds. And that's why we want to have multiple water circuits, because different plants will have different requirements. And there you have it for the water plumbing. Thanks for watching my video. Feel free to leave comments, and maybe if you even have a feature request for additional capabilities of a system like this, maybe I'll buy some parts and tinker and demo that. But thanks again for watching. Namaste.